Gas chromatography, GC, detailed explanation. 1. Introduction to gas chromatography, GC. Gas chromatography, GC, is an analytical technique used to separate, identify, and quantify volatile compounds in a mixture. It is widely used in chemistry, biochemistry, forensic science, food analysis, and environmental studies. 2. Principles of gas chromatography. GC operates based on the partitioning of analytes between a mobile phase, carrier gas, and a stationary phase, coated inside a column. The components of a mixture travel through the column at different rates, leading to their separation. Basic components of GC. 1. Carrier gas, mobile phase, an inert gas such as helium, nitrogen, or hydrogen that carries the sample through the column. 2. Injection system, introduces the sample into the system, usually in liquid form, which is vaporized immediately. 3. Column, stationary phase, a capillary or packed column coated with a liquid or solid stationary phase that interacts with analytes. 4. Oven, maintains and controls temperature, which affects analyte separation. 5. Detector, identifies and quantifies separated compounds. 6. Data system, processes and records chromatographic results. 3. Types of gas chromatography. 1. Gas-liquid chromatography, GLC, the stationary phase is a liquid coated on an inert solid support. 2. Gas-solid chromatography, GSC, the stationary phase is a solid adsorbent material. 4. Sample injection techniques. 1. Split injection, a small portion of the sample enters the column, and the rest is vented. 1. Used for concentrated samples. 2. Splitless injection, the entire sample enters the column, suitable for trace analysis. 3. Direct injection, injects the sample directly into the column. 4. On-column injection, introduces the sample directly into the column without vaporization, used for thermally unstable compounds. 5. Types of GC columns. 1. Packed columns, filled with a solid stationary phase, used for large sample volumes. 2. Capillary columns, long, narrow tubes with a liquid stationary phase, providing better resolution. Capillary column variants. 1. Wall-coated open tubular, WCOT, liquid stationary phase coated on the inner wall. 2. Porous layer open tubular, plot, stationary phase is a porous solid layer. 3. Support-coated open tubular, SCOT, a support-coated inner surface holds the stationary phase. 6. Carrier gases and their selection. 1. Helium, He, most common, chemically inert, and provides good efficiency. 2. Nitrogen, N, offers high efficiency but slower analysis times. 3. Hydrogen, H, faster and cheaper but requires safety precautions. 7. Detection systems in GC. 1. Flame ionization detector, FID, detects organic compounds based on ionization in a hydrogen airflame. 2. Thermal conductivity detector, TCD, measures thermal conductivity changes of the carrier gas, used for inorganic gases. 3. Electron capture detector, ECD, sensitive to halogenated compounds, used in environmental analysis. 4. Mass spectrometry, MS, provides molecular identification and structure analysis. 5. Flame photometric detector, FPD, detects sulfur and phosphorus compounds. 8. Factors affecting GC separation. 1. Boiling point of analytes, higher boiling points require higher temperatures. 2. Column length and diameter, longer columns provide better separation. 3. Stationary phase polarity, affects interaction with analytes, impacting retention time. 4. Carrier gas flow rate, influences peak sharpness and separation efficiency. 5. Temperature programming, affects analyte elution and resolution. 9. Advantages and limitations of GC. Advantages, checkmark high resolution and sensitivity. Checkmark rapid analysis. Checkmark can separate complex mixtures. Checkmark wide range of detectors available. Limitations, multiply limited to volatile and thermally stable compounds. Multiply requires sample preparation. Multiply destructive analysis, in most detectors. 10. Applications of gas chromatography. 1. Pharmaceuticals, drug purity and stability analysis. 2. Environmental science, detection of pollutants, pesticides, and VOCs. 3. Forensics, analysis of explosives, drugs, and toxins. 4. Food industry, identification of flavors, preservatives, and contaminants. 5. Petrochemical industry, composition analysis of fuels and hydrocarbons. Conclusion: gas chromatography is an essential tool for separating and analyzing volatile compounds with high precision. Proper selection of columns, detectors, and operating parameters ensures optimal performance for different applications. Subscribe.